A particle moves in a straight line and its position is described relative to some origin O by the equation x of t is equal to t cubed minus 3t plus 1, where the distance is in centimetres and the time is measured in seconds for t greater than or equal to 0. So as you can see, as we let t go from 0 onwards to positive numbers, the particle moves up and down this line here, which is its position, which we might call x. We then graph it against time, which gives us this blue curve, which we can label as being x of t, and we know what the rule is for that. Over here, the simulation gives us an indication of what's happening to the particle, so it tells us the direction and whether it's speeding up or slowing down. So for the first part of the journey, you can see that the direction is down and that it's slowing down. We can then see at some point the direction changes and it starts speeding up. So we can unpack the idea of a particle slowing down and speeding up by inspecting the acceleration graph, which is this graph here, which could be a of t, that describes the acceleration, and the velocity graph, which is this graph here, so that's v of t, and that describes the velocity of the particle. So as you can see, for the first part of the journey, we can see that it has a negative velocity, but a positive acceleration. So that means that we would expect the particle to be slowing down. So for 0 to 1 second, it's actually slowing down. And that's because the velocity and the acceleration have opposite signs. However, as we continue it, we can see that it's actually speeding up. And that's because we now have a positive velocity with what will be a positive acceleration up here. So when the acceleration and velocity have the same sign, that means that we're going to see a particle speeding up. So up here, it's actually speeding up. And that's going to occur for all t greater than 1. If we watch the particle once again, we can see that the particle goes down, 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 and then it changes direction. And that occurs when we reach this minimum on our graph x of t, so this minimum down here. And that change of direction is a stationary point, which means that the derivative v of t is equal to 0, and that occurs when t equals 1 on this graph. And then once the particles change directions, it continues in the upwards positive direction for all t greater than 1. So that's a brief look at a simulation of what's happening to this particle. Now we're going to go on and have a look at some questions that we can answer about it. Now we want to find, for part A, the expression that describes the velocity of the particle. So the velocity is equal to the derivative of x of t, the position of the particle. So x dashed of t is equal to v of t, which is the velocity of the particle. And that's going to equal, and we can use our rule that takes the power at the front and 1 off the power to derive this. So it's going to become 3t squared minus 3. So that's an expression for the velocity of this particle. For part B, we want to find the expression that describes the acceleration of the particle. So by taking the derivative of the velocity, v dashed of t, we find an expression for a of t, the acceleration, and that's going to equal, and using our power out the front, 1 off the power rule, this just becomes 6t. So for part A, we found an expression for the velocity, and for part B, we found an expression for the acceleration of this particle. For part C, we need to describe the position, velocity, and acceleration of the particle at t equals 2. So first off, we'll find the position. So that's the x function. So x when t equals 2 is equal to 2 to the power of 3 minus 3 times 2 plus 1. And when you evaluate that, you should find that it is equal to 3. And when you evaluate that, you find that that is equal to 3. So the interpretation that we can make is that the particle is 3 centimeters from the origin in the positive direction. Next, what we're going to do is find the velocity when t equals 2. So that's going to be the same as evaluating the function v at 2. And when we do that, that is equal to 3 times 2 squared minus 3. And when you evaluate that, you'll find that that is equal to 9. So the interpretation of that is that the particle is travelling at a speed of 9 centimeters per second in the positive direction. Finally, we need to find the acceleration, which is going to be a evaluated at 2, and that is going to equal 6 times 2, and when you evaluate that, you'll find that that is equal to 12. So interpretation of that is that the particle is accelerating at a rate of 12 centimeters per second in the positive direction. For part D, we want to find the time and the position when the particle changes direction. So to find the time when the particle changes direction, we're going to solve v of t is equal to 0. So that's when the particle is stationary, meaning that it stopped moving in one direction and it's changed to move in the other direction. So therefore, we're solving the equation 3t squared minus 3 is equal to 0. And to solve that, we can start by adding 3 to both sides of this equation. And we find that 3t squared is equal to 3. Dividing both sides by 3 will give us t squared is equal to 1. Therefore, t is equal to plus or minus the square root of 1, which is still simply 1. However, time is a positive quantity. Therefore, we can write t is greater than or equal to 0, which means that the only solution we get is t equals 1. Now that we have the time when the particle changes positions, we can find the position by evaluating x of 1, which is simply equal to 1 cubed minus 3 times 1 plus 1. And when you evaluate that, you find that that is equal to minus 1. So our interpretation is that the particle changes direction after 1 second when it is 1 centimeter from the origin in the negative direction. For part E, we want to state the intervals of time t when the particle speed is either increasing or decreasing. So if we first consider the case when the particle speed is increasing, we need to recall that the speed will be increasing when the velocity and acceleration have the same sign. So that is, they're both positive or they're both negative. So from the graph over here, you can see that the acceleration is always positive for t greater than 0. However, the velocity graph, which is in red, goes from negative to 0 to positive. So the time interval where they're both the same sign is when this velocity graph is positive, which is t greater than 1. And the acceleration graph, if we graphed it up here, would also be positive. Therefore, the particle's speed is increasing when t is an element of, and it goes from 1 not included because at 1 the velocity is 0, all the way until infinity. So anything greater than 1, this particle speed is increasing. For part 2, we're going to have a look at when the particle speed is decreasing, and this occurs when the velocity and acceleration graphs have different signs or opposite signs, so one being positive and the other being negative. So on the graph to the right, you can see that the velocities graph is negative down here, while the accelerations graph is positive up here. Therefore, the particle speed is going to be decreasing for t is an element of 0 not included until 1 not included, and that's because the acceleration and velocity graphs will have the opposite sign, one being positive, one being negative, over that interval. Now you will note that we've used a round bracket here, and that's because when we take the derivative of the position function and the derivative of the velocity function, it won't actually exist at the endpoint. So this would be an open circle on the graph, and this would be an open circle on that graph. So that point's not included, so we use a round bracket to indicate that. The round bracket here is because at that point the graph is stationary, so it doesn't have a positive or negative velocity at those points. So we use round brackets for both of those brackets.